Jim, it's Tommy. I just want to do a quick audio check. Do you want to unmute, just to make sure everything is okay? Chad, I saw you on mute. Can you do a quick check?
Yes, I'm good. I can hear you.
Thanks. Sounds good.
Yep.
Jim, not sure. I'm going to try again. If you're there, if you could hear, unmute and just do a quick audio check. Liang, can you do a quick audio check, please?
Yes, can you hear me?
Perfect. Thank you.
Yeah, hi, Tom. It's Jim. You can hear me okay?
Thank you. Yes, I can hear you.
Okay, great. I'll mute again.
Yes. Chad or Liang or anyone, can you guys see the presentation okay?
Yes, I'm fine.
Perfect. Okay. All right, we'll start in about 20 seconds. I see people coming in, and I'll give a couple people some time to get situated, and then we'll begin. Okay, we're going to begin. Good morning, everyone. I want to welcome you to the NHERI Lehigh virtual workshop. Logistically, just want to make a few notes that we're going to have question and answering sessions between each session that you're going to see in the agenda soon. We would ask that people please keep yourself on mute and only unmute during the question and answer sessions, or you could put your question in during the sessions on the group chat. And at the end of the presentations today, we can have an open forum to discuss any other outstanding questions that were not addressed during the Q&A sessions. So at this time, I would like to turn it over to Jim Rickles to open up and welcome everyone to the presentation, to the workshop today. Jim, you need to unmute.
Sorry, I'll repeat myself. I apologize. Good morning, everyone. Want to first welcome everyone and thank you for joining our workshop, whether you're wherever you are in the world. It may be in the afternoon or in the evening. Basically, our workshop is being held virtual because of the current situation, and we have a 2.5-hour workshop. So we're going to be a little bit coarse in terms of we can't go to the depth that we normally would like to within that time span. So what I would encourage you to do is if you have questions, go ahead and pose those. You're always welcome to contact us after the workshop. You're always welcome to come visit us. In doing so, we typically have hands-on experiences in terms of actually going into the lab. So we'll try to convey as much of that as we can virtually. Okay, so with that, Tommy, how do I begin then with the presentation here?
Just normally at the bottom of the Zoom, you should have your share screen button and share your presentation.
Okay, I thought you were gonna do the thing there. So I need to bring up my PowerPoint here?
Correct.
Okay.
Just a reminder, everyone presenting is going to present their own PowerPoint presentation for logistics reasons. Makes it easier.
Sorry about that. We planned ahead of time, but had some last minute changes here. So again, going to welcome you.
We can see your screen. Perfect.
Okay. The agenda will follow as we see here. I'm going to present the objectives and the science plan, followed with a description of our facility in terms of the capabilities, physical layout, and also the protocols being the experimental approaches we take towards, and numerical approaches we take towards simulations. And then complete that with some example projects. So what I'll leave off is a few of the projects that then Dr. Liang Cal will follow up after a Q&A And that presentation by Liang will be associated with hybrid simulation, some of the framework, the hardware and software capabilities. We've worked on this problem for over 20 years, so we want to show you some of the latest things we've worked on. And then later, after the Q&A, we'll go ahead and continue with IT infrastructure. Thomas Murillo, who you've met there, we'll talk about that, and then we'll wrap things up with Chad Kusko, Dr. Kusko, on site operations and payload opportunities, and have a final Q&A with a wrap up. I think what I'd like to do at this point is I think you can see people on the video, and I'm actually looking on the screen and my camera's off to the side, so I have to apologize, but I'd like to introduce the other people, just have them say hello, and we could then continue then with the actual presentation. So again, my name's James Rickles, formerly I'm the director and the PI of the facility.
I'm Chad Kusko. I'm the operations manager for the NHERI Lehigh facility.
I'm Thomas Murillo. I'm the systems administrator at the NHERI Lehigh facility.
Hi, I'm Liang Kao. I'm the NHERI research scientist.
Okay, yeah, so thank you very much. And unfortunately, we don't have time for everyone to introduce themselves. Normally we would do that in the workshop, so you get to know each other. But we will have everything archived, including the participation list, so you'll have access to that information and ways to interact and meet. You may find a common denominator amongst yourselves for some of the opportunities we offer, and that would be a good thing to collaborate amongst yourselves for that purpose. Well, let me begin with the objectives. So we have 5 objectives listed here. The first is to provide you with information on the capabilities of our facility for advanced natural hazard engineering research. What we are going to do is describe our new capabilities, as well as the older ones, and the resources available for conducting research. We'll also include the procedures to perform the large-scale experiments using our facility. And I'm going to be sure to relate this to the science plan and how the NHERI, Natural Hazards Engineering Research Infrastructure, RTND stands for Real-Time Multi-Directional, EF is Experimental Facility, enables key research in emerging areas of natural hazard engineering. And then finally, to explore opportunities to use our facility for unsolicited career and other types of NSF proposal. Our goal is to have researchers to submit NSF proposals. Basically, those grants that they're awarded, we're able to support essentially at minimal of no cost for you to do the research here at our facility. The only thing you'd have to really pay for is the construction of your specimen. So let me begin with the science plan. We provide a next generation, we always try to stay ahead of the curve, multi-user facility to perform transformative research, closely integrating numerical and experimental simulations to advance natural hazard engineering research and education, thereby enabling the challenge of community resiliency to natural hazards to be met. And this is through a couple of aspects here. Improve concepts for renewal and retrofit of the built environment, that is resiliency, exploitation of new emerging materials, the development of innovative, resilient structural concepts, economical design approaches towards natural hazard mitigation, and the development and validation of more accurate physics-based computational simulation models. Our focus is on large-scale, multi-direction, real-time hybrid simulations. And as you'll see later, that's not the only thing we do, but we'll elaborate on that later. But in this type of simulation, you combine physical and computer-based simulations. An experiment is actually a simulation, it's just a physical phenomenon, but we combine that with the computer-based for evaluating the performance of large-scale components and systems as a whole. The thing that we do, and we want to be sure that this doesn't appear to be overwhelming, because real-time hybrid simulation on paper looks not too difficult, but when you get into the details and the theory, it could be a little bit overwhelming. What we do is we provide user-friendly tools that will enable you as a researcher to readily utilize maybe advanced methodologies that we've developed using advanced testing technology and the algorithms to perform complex experiments. And we'll show some examples of that as we proceed through the presentation today. So what we're able to do is enable researchers such as yourself to readily perform 3D real-time hybrid simulations, RTHS, of large, complex, nonlinear systems, not linear, but nonlinear systems subjected to multi-natural hazards, example being wind and earthquake, using analytical substructures created with robust computational models. Also, 3D multi-hazard real-time hybrid simulations of systems with numerous response modification devices, where we use model updating in order to expand the realm of what's being physically defined, what's being numerically defined by using the experimental measured quantities to improve the numerical part of the simulation. I'll explain the details of hybrid simulation conceptually here in a minute. Accurate large-scale 3D multi-directional experiments. You have nonlinearities between actuator motion and specimen motion, and this could be in quasi-static, hybrid simulation HS, or in real-time RTHS, that involve these nonlinear kinematics with both the actuator and the specimen. And in doing so, you need to have accurate actuator control. So we have the ability to do that with some of the algorithms that we've developed, enable you as a researcher to utilize them involving 3D simulations. Some key questions in natural hazard mitigation. These are ones that have been posed by the National Science Foundation, the NHERI Science Plan. Some of these which can be addressed through research performed at our facility will lead to the development and implementation into practice new natural hazard mitigation strategies and innovative resilient structural systems. In other words, the research that you perform will transform and translate into practice. That's one of the ultimate goals. In addition, enhance understanding of response to multi-natural hazards by accounting for soil structure interaction and fluid structure interaction effects. We actually look at considering both. Then the comprehension of system level effects on structural and non-structural components to these large-scale 3D system experiments, not just one isolated component, but indeed the whole system in 3D. Acquiring high-quality data, again, leading to improved computational models for predicting essentially the response, not just of a system, but perhaps a lot of the infrastructure at the community to natural hazards. And what's very important there is training the next generation of workforce. What we mean by that are the students who will become then the leaders of tomorrow in natural hazards engineering. What are some example projects? We have a number of them. These are just some that could be enabled. Some of these don't exist yet, but could be enabled. At our facility, autonomous semi-active controlled devices for achieving resilient performance of structural systems and multi-hazards. An example, this would involve, say, real-time hybrid simulation. Promoting resiliency again, but using shape memory alloys in terms of advanced bracing systems. Quasi-static or hybrid simulation could be used. Going to looking at smart systems, again, multi-agent replica control methodology, so control algorithms that are semi-active for sustainable vibration control of smart building structures. Looking more at materials, this is advancing computational modeling of structural damage and reinforced concrete subjected to complex loading histories, through multi-directional mixed mode, hybrid simulation or quasi-static. Quantifying seismic resiliency of multi-functional floor isolation systems through cyber-physical testing, hybrid simulation, in this case real-time because it's probably rate dependent. And performance of non-structural components, very important as part of the issue of community resiliency. And so these components are in systems and we want to minimize the multi-hazard losses of these. And the effects of soil structure foundation interaction and multi-hazard forms of tall buildings, supplemental damper outrigger systems. And the last one I have here is semi-active controlled cladding panels for multi-hazard resilient buildings. And in the parentheses, I didn't name each of the methods, but those are some perhaps conceived methods that could be pursued. This may be a little bit choppy. I don't want to talk much, but this is just sort of a vision. On the left is a 40-story building subjected to 110-mile-an-hour wind. Same building on the right subjected to a max considered earthquake. Just looking at the multi-hazard response of the system. When the system subjected to wind is permanently linear, but it has high acceleration, so there's dampers placed in to minimize that. At the same time, on the right-hand side, when the earthquake occurs, it's actually not only response in the braces that that take place. So this example with nonlinear response is accounted for. Let me now describe the facility. We're a former NHERI site for, I think it was 2002, actually originated from 2014. We've continued as a NHERI site. We were looking at primarily earthquake, now we're at basically natural multiple hazards in general as a NHERI site. We're unique in that we have a portfolio of equipment, instrumentation, and infrastructure, in addition to test beds with simulation protocols that enable us to do experiments for large-scale multi-directional testing. We could conduct concurrent multiple large-scale experiments, not just one, but several of them because of the size of the laboratory. We have an experienced staff that's very important. And our facility exists within what's called the Atlas Center. And the Atlas Center has been at Lehigh since 1987. It was sponsored by NSF. It continues to thrive, and that gives us additional resources and infrastructure to work within, but also we complement, that is NHERI, our facility and Atlas complement each other. This is a picture of the Atlas Center, the building. You're always welcome to visit us. You can kind of get an idea about the size from the fact that you see the cones on the left are about 2.5 feet tall, and the size of the building. That's where the high bay lab is, where we perform the simulations behind those walls. What are our strengths? Well, I mentioned this a few times, large-scale multi-directional testing, real-time loading. We have the actuators, hydraulic power to do so. We also have the ability to control those actuators, including adaptive compensation. That's very important in hybrid simulation because you can't really pre-tune things very well, being at the state of not only the actuators going nonlinear, the sort of hydraulic, but also the specimen, and that could change your control parameters if you try to fix those otherwise. We've built hybrid simulation from the ground up. You know, we didn't borrow something and then try to run it. Basically, it doesn't lend itself towards what we'd like to try to accomplish. So we've implemented integration algorithms, formulated those initially, developed analytical models, multi-grid, that's parallel processing type approaches, actuator control, multi-directional, real-time actuator control in addition to kinematics, online model updating, and a data model for large-scale test data. Our facility includes instrumentation, the conventional instrumentation, but also the advanced instrumentation such as digital image correlation. I think you'll see some examples here later, as well as laser transducers. And we have a large inventory of Atlas testing and auxiliary equipment beyond what we have for the NHERI. And that allows us to basically complement and have some contingency and redundancy. Now, the people are very important. So our team includes expertise in several areas, including structural, earthquake, geotech, aeroelasticity, and wind engineering. Also in the areas of hydrodynamics, fluid suction interaction, probabilistic-based modeling, and structural monitoring and damage assessment. We're pioneers in real-time hybrid simulation. We have a good know-how in large-scale experiments. On paper, it's one thing, but to be able to have done it successfully and have the experience that lends itself towards helping researchers and do this is very important. That's the know-how. And we have a strong relationship with industry, practicing engineers, and familiarity with codes and standards. Myself, I'm a registered practicing professional engineer, so I'm very familiar with the practice and the field. And again, experienced laboratory staff, I can't overemphasize that. Here is a picture of our staff. I'll call it the Lehigh team. You've met myself in the first row there at the top. Richard South is a co-PI. He's actually the director of Atlas. I direct the NHERI facility, so together in harmony, we oversee the operations. On the second row here, you've met Chad Cusco, Leanne Cow, and Thomas Murillo. Want to note here, Derek Fitchman is the lab manager within Atlas that basically has the cohesion of having the staff, the laboratory staff, of which we have 6, help carry out the experiments by constructing and placing instruments, etc. Now, these different areas of expertise I mentioned earlier are through our capacity building partners. We're always looking to advance and raise the bar. So Justin Jaworski, Mohammed Suleiman, Paolo Pacini, Jermaine Paxad, and Narimdan Banerjee are expertise in areas that I've identified there. Some of them are in other departments. We have them actually at Lehigh primarily because we have a close relationship with them, but we always look to interact with people outside of our university, of course. We're not by any means a closed society or door. So with that, let me then describe our protocols, experimental protocols. First, what is hybrid simulation? I'm only going to give a brief overview and a schematic, and Leanne Cal is going to go through some more details, particularly some of the algorithms, just give you an overview with some references. Well, let me try to describe it, and just again in a very tourist manner here. Let's relate this to a project that was ongoing involving wind loading. In this case, going to be predefined. You may argue, well, that's not going to need fluid structure interaction. I'll argue, yes, in general, but the structure at 110 mile per hour wind loading, the velocity is 110 miles an hour, and the structure only moves about 1 or 2 miles an hour. So in this case, the predefined wind loading is certainly justified. So going back to that 40-story building, you saw the video before on the left side of the screen. We actually conducted wind tunnel testing, a 3D test. You see the FIU, that's Florida International University. You also have a NHERI facility called the WOW, Wall of Wind. Performed wind tunnel testing there on the scale model of the structure. We have nonlinear viscous dampers in the outriggers that exist in the structure in order to alleviate the accelerations and also try to improve under seismic loading the seismic response. But here, let's just focus on the wind. So we're going to discretize that system because we can't fit a 40-story structure in the laboratory. Our height over ceiling is probably about 70 or so feet. So we're going to place a numerical model called the analytical substructure, everything we can comfortably model analytically. And this is full scale. And the residual of the structure, which we feel we need to model physically, is the experimental substructure, as it's called, the dampers. These are nonlinear viscous dampers. You may argue, no, there's simple, very easy models, nonlinear Maxwell models, as an example. I would argue no, because these dampers perform differently under earthquake or wind, and being large scale, there are some issues there that you may be surprised about. So this is a simulation coordinator. It integrates the equations of motion. This is numerical integration. This is where the integration algorithm is very, very important. Leanne will discuss later. You have the inertia, proportional acceleration, velocity, which is going to relate to the inherent damping. And R sub A is the restoring force from the left-hand side analytical substructure. R sub E is from the experimental substructure, the restoring force. That all balances the applied load. So at a particular point in time, we're going to take the forcing function, the point in time, and put that into the coordinator. And then the equations are going to be integrated such that they'll produce command displacements to both substructures. They'll be separated out as shown. And what we ask in return is to have those come back. And this needs to be done in real time. Example maybe being less than 0.002 seconds. And we've actually done simulations where this is taking place less than 0.001 seconds. 1 times 10 to the minus 3 is a time step. That all has to be completed within that time frame. And so if you're able to do that, you then would go to the next time step. If you can't do that, the experiment's just going to go berserk because you create energy, which you know is literally impossible, but the system will try to do that and it will basically diverge and become unstable. So if you go through that whole process and you finish the experiment, you've got a real-time structural response. If you slow down the rate of testing, and that would be fine as long as the right-hand side experimental substructure is not rate dependent, you would have basically a more conventional hybrid simulation. So just a brief overview. Lane Cal will elaborate more on this later. So in terms of some of the capabilities, we've got some large-scale real-time hybrid simulations. RTHS is the abbreviation example shown on the right. We've actually got 2 bays, a moment frame and a braced frame. We have hybrid simulation where basically it's just an expanded time scale. Things are slowed down. Why the difference? Well, if in the laboratories they're not rate-dependent specimens, then there's no need to speed it up. You can slow it down, which is what's shown here. This is a self-centering, moment-resisting frame, basically made out of steel, not too rate-dependent. Nothing's welded there. We can also have multiple experimental substructures rather than one. The example on the right shows 5 actuators. Those are the blue cylinders connected to dampers. The dampers here are positioned at different locations in the building. We could also distribute the simulation. It's called geographically distributed. We've done this internationally as well as locally. Example here being with University of Illinois, RPI. versus modeling soil in a centrifuge and Lehigh ourselves. And the simulation coordinator in this case was at the National Supercomputer facility located at UIUC, University of Illinois, Urbana-Champaign. We can also do this in real time. We've done so, and I'd like to acknowledge Dr. Kim and Dr. Richard Christensen at University of Connecticut, who we've interacted with and were able to do this. Now, we do more than just hybrid simulation, real time or slowed down. We can look at predefined load or displacement. You may be very interested in looking just at quasi-static testing or just characterization. Examples here showing dampers. There's a smart damper, there's a MR semi-active control damper and the characterization test. The lower right is a temperature chamber, which we're looking at, sorry, not viscoelastic, but elastomeric dampers and looking at the effective temperature. It could be also a large structure, just a coupled shear wall with post-tensioning, reinforced concrete. Also dynamic testing. Dynamic testing in this sense is predefined motions. This is multi-directional dynamic testing to evaluate the performance of couplers in a pipe system for distributing water throughout a structure. This may be more thought of the non-structural component. And we also have the ability to look at storm surge as well as tsunami surge debris, the impact that could be developed as a result of that with structural systems, harbor type facilities. And also soil structure interaction. This shows a soil box here. Now the lab, those capabilities are created from within the laboratory, the Atlas laboratory. Shown on the right is a strong floor, strong wall system called a 3D high bay structural testing lab. The dimensions are shown as up to 50 feet tall at the far end with anchor points at 5 feet. The strong floor is 40 by 100 feet. This is in imperial units, so if you want to convert that into the metric, you divide it by what, about 3 roughly. We have a hydraulic supply system, additional over 30 hydraulic actuators, and supplementing what we have just from our NHERI facility of additional digital controllers, acquisition systems, a large array of conventional sensors, including those advanced sensors, and auxiliary equipment, an example being a 40 kip crane that we can use to lift things in place. Now, what complements that is our NHERI equipment. This was what was purchased from our sponsor to outfit our lab to be able to do what we are showing you we can do here. What's important at the heart of the matter is the hydraulic equipment and the power. Basically, we designed this back in 2002 to enable real-time, large-scale earthquake simulations to be simulated, if you wish, and the demand imposed for up to 30 seconds or longer. Okay, this involves having a hydraulic supply system. We have 5 120 GPM pumps, an accumulation system to augment that. We can basically supply over 4,000 GPMs. That's gallons per minute. We have 5 dynamic actuators. The capacities are in imperial units, 517, 382 kips. Stroke plus or minus 20 inches. And the maximum velocities are 45 inches a second and 33 inches a second. This was all by design. This is achieved through high flow servo valve that we could rearrange on the actuators shown in the lower right. The blue cylinders are the actuators. Now, we can combine those resources to basically, as I mentioned, multiple concurrent projects, and some examples are shown here, which we'll describe some of these later, but real-time hybrid simulation, a hybrid simulation, quasi-static and hybrid simulation, and quasi-static simulation of different specimens, different projects. These are actually all currently ongoing. We didn't necessarily test exactly at the same moment in time, but we have these as current projects able to have the researchers in the lab concurrently. Tommy will talk about our integrated control system that's on the IT side, but what I want to allude to here is it's a real-time system in which we configure those protocols that I referred to earlier, and they're shown here. And I want to make sure this is emphasized here. We can run the experience in real time, and some examples there that may exist, or we can basically slow them down. We call it an expanded time scale. So you don't want to feel like, well, I'm only going to go to Lehigh if I'm going to do a hybrid simulation in real time. So no, if you want to do any type of testing at large scale involving impose motions. Doesn't matter at the rate of loading. It could even be a very, very slow test. We could accommodate you. We can also accommodate server hybrid simulation via custom software. That's a second bullet item, or OpenFresco you may have heard of, that was developed at Berkeley. We use both of those pieces of software. And we also have a very flexible system in which we can use software middleware packages developed by the users or the NHERI cyber infrastructure. That's an entity in the NHERI community. They can be plugged and utilized, but we just don't plug them in. We want to be sure they work and they've been validated, but we can integrate that into our system. Some other resources that exist. We have a large preparation area for constructing specimens. There you can see a braced frame that was actually fabricated. It's about to be lifted into the test bed. We do mechanical testing for materials. We have an auditorium for education and community outreach activities. The preparation areas include not just a staging, but also a machine shop. The laboratory I showed there is a mechanical. We also have intelligent structures. That's for health monitoring, welding and joining materials, and microscopy. We have offices for visiting research, essentially faculty and staff as well. And the meeting rooms I allude to, but also we have conference rooms. Storage areas, and this facility is definitely secure, that you can feel your things will be safe. Let me now describe the test beds. One of these is the large lateral force resisting system test bed. Those are the dimensions that we could accommodate for lateral resisting systems. These can be basically ones in which we develop, say, information characterization tests or real-time hybrid simulations. It's the right-hand side, you see the picture of that. We have also a non-structural component multi-directional seismic simulator, a photograph shown on the right side. The dimensions are shown there. It's multi-directional, again, for either characterization or if you want to do hybrid simulation. The damper test bed, you saw a picture of this earlier. The capacity of those is really based on the actuators, which again, I'm just repeating here. And we've used those test beds for characterization as well as real time. And I should note, these test beds could be reconfigured and positioned at different locations in the laboratory. The tsunami and storm surge debris, I mentioned that. It basically consists of high-speed cameras and a high-speed data acquisition system, very high bandwidth resolution load cells to be able to measure the impact force. And we have accelerometers and laser displacement transducers to be able to achieve that. The soil box is a reduced size scale soil box. It's very good for pilot tests. Enables one to look at the interaction between the structure and the soil. The dimensions are shown there. It's got advanced sensors as well as the conventional sensors, including actuator load cells. The fact that we could also use this to do hybrid simulation or just conventional characterization tests is an attribute. And something that's new, we promised this in the objectives of our workshop. We created a real-time cyber physical laboratory, structural systems laboratory. What we have there is MTS equipment that is used to basically create this laboratory. Shown here are 5 actuators and test beds here. And it's a new resource. It's created to enhance our ability to conduct additional research, tie it with ECO activities, and training. Researcher training, we get hands-on experience. So if the other equipment is being used, which we're quite busy, but we always make the time to make sure researchers have access to it, whether it's training or for the actual research. This gives us additional options. You can get hands-on experience in cyber physical systems. That's sort of a new coined term for hybrid simulation. The goal is to broaden the knowledge, but primarily the user base. It's a smaller scale, lower cost with test beds. So the budget, if you running a proposal, wants to be as large. And I mentioned creates hands-on options here. It's very good for creating pilot study, for obtaining data from pilot studies, for even developing a proposal. We use it also for capacity building. The system itself, before I state some of the equipment, is in terms of the integrated control systems, identical to what we have in the laboratory of the big actuators. Nothing's different except here we just have a different set of actuators. The particular actuators there, they're model numbers there. I think they're guests from MTS would acknowledge what those are. I'm just going to list these down here. We design those in order to get long strokes, such as, we're looking at hybrid simulation with shake tables, so we have a very long stroke actuators, in some cases plus or minus 10, versus some shorter stroke actuators will be greater capacity, but then also very high velocity. So this is envisioned to look at maybe some different ranges of demand. Now you can find further, and I realize I'm going a little bit fast, this is of course going to be archived, but you could find additional information on our equipment or the portfolio that are protocols on our website. So I'll point you towards that, and Chad will talk about some other aspects on this page, including the payload project noted at the bottom of this slide. So with that, we'll have a Q&A after I finish this next session there. This will be on some of the example research projects. There's a long list here. This is archived, so I'm not going to go through and read. I'm not going to go through and look at every one of these, but rather I'll select a few of these. But we have the researcher, the institution. Sometimes we collaborate with other institutions, primarily because they like us to help out with maybe some of the hybrid simulation, but typically those are led by other researchers such as Shailene Pei. This is the title of the project. In parentheses is the methodology. So I'm going to go through some of these, and I'll let you study this on your own if you wish. The most recent project is by Scott Harvey, who was here 2 weeks ago, and in that 1 week we did 240 hybrid simulations on a base isolation system. So first project is the one directed by Simon LaFlamme, Iowa State. It's looking at semi-active controlled panel cladding. These are connections to improve the performance of the system. Basically, the hazards include earthquake, wind. So it involves different facilities, has ourselves, the NHERI UF and FIU, or University of Florida and Florida National University, their wind tunnel facilities. Mentioned cladding connections control laws. The scope included constructing the prototype connectors, performing characterization tests, and then having that and models derived from that, performing large-scale hybrid simulations in real time to validate the numerical models and really the performance and the ability for these connections to improve the overall performance of the system. The wind tunnel facilities are both involved, shown here. The right side shows some hybrid simulation results. I think you saw these already. Some of the findings there, we found the semi-active controlled cladding connections can indeed improve the performance. Some numbers are shown here in which the reduction is shown relative to not having the devices in the structure. In this case, it was an LQR semi-active controller that was used here. Here are some acknowledgements. Leanne Cowell, if you have any questions, could elaborate on those later. Now, what complements that project is where we looked at passive energy dissipating cladding connections combined with supplemental damping systems. And so example being, there's a friction damper. This is a new generation rotary friction device. Leanne Cal actually has been leading this effort. We also have nonlinear viscous dampers, the latter being in tall structures. Wind tunnel testing, of course, was involved for the wind aspects. Some of the findings, again, we found that particularly the outrigger systems with nonlinear viscous dampers, you can have significant improvement. It's all, I guess, relative to what you say is being significant, but this is a relative improvement here in terms of comparing without this, the damper systems. Here are actually the dampers under wind. The scales aren't the same under earthquake. They perform linearly here, and here they're actually performing nonlinear, as evident by the capping of the force. Again, they're not the same scale, apparently, because we want to get them on the same page. The other thing that's very important, I've seen this written up many times, but we've discovered this a while back, but just reinforced it here, is that the load path is very important that the dampers reside in. And you want to make sure in the load path, the dampers are basically, their relative stiffness is sufficient that the deformations will be occurring in the dampers and not in the members that basically otherwise are in that load path in series. Otherwise, the dampers are not effective. This video you already saw here, this actually has torsional response. You see there under the wind loading, and the dampers are actually reduce the accelerations by almost a factor of, I think it's close to 2. Laney will comment on this later. Colorado School of Mines, we looked at resilient systems made out of timber, cross-laminated timber. This is led by Shailene Pei at Colorado School of Mines again. Involved rocking systems. These are post-tension, self-centering, cross-laminated timber walls, CLT, ST stands for self-centering. Particular studies done in Lehigh was to construct those walls and the floor system and the collection system and the gravity load system and subject that to bidirectional loading. This was quasi-static in order to look at the details that have never really been developed or validated, the actual details of the connections, the gravity connections, the collector connections, and the performance of the walls. This is a new concept here. Involved large-scale testing again. It actually had 3D motions because things were done in the bidirectional prescribed motion, but the vertical motion occurred because of the fact that the members, when they were displaced laterally, they also tended to move downwards because of the kinematics. Enables us to develop high-fidelity computational models of our collaborators. Again, led by Shailene Pei, is a larger collaborative project in which this is going to lead to a large-scale shake table test at UCSD in September, I think it's of 2021. It'll be a 10-story structure. The 2-story structure has already been completed. This just shows some pictures of this, a rendering. This is the actual test itself. There's probably, I think, 4 or 5 phases of this, which is, I think, phase 2. This shows the DIC system being used on the shear wall. There's a couple of shear walls. One of the shear walls here is got the instrumentation attached to it. Some of the structural details, the collector beams, the gravity connections. This is at 6% drift. And underneath, I think this is at the beginning of the test. We don't see it drifting here. This is the kinematics. We've derived the exact solution back in 2000, I think it was, with Orion Machan, and lately Ali Amir, current PhD student, translated this to 3D, but these are some of their kinematic relationships, and with instrumentation carefully arranged, we can measure the 3D motion. That's not only used for measuring response, but also actuator specimen control. And here you can see as the specimen moves laterally, it also is shortening because you can see the difference in the distance here that attests to that. This just shows a video split screen where the red and blue in the lower left is showing measured versus targeted. We're able to achieve very, very precise motion control, and you want to be able to move the specimen to exactly where you want it to be so you can get the data you need. This is at the base of these 2 coupled shear walls shown here. And this is a hysteresis. In plane, you expect more lateral force versus a drift versus out of plane. It's not intended to be out of plane. Notice they primarily self-center. There's a little bit of residual. That's because of the wood here developing some damage, which we've improved that behavior by reinforcing it. Now, Kerry Ryan at University of Reno has been doing testing, which is looking at the non-structural. So the structural part we can make resilient. The weak link in the chain of resilience becomes the non-structural. She's been looking at, for instance, here, partition walls. So here are some partition details. These are subjected to bidirectional loading by placing it in our setup, as shown here, and subjecting it to the bidirectional loading to see if these components will be able to remain resilient, but also how much do they contribute to the structural response? They're not just going for the ride. And this is attested to here, where this is the force versus drift, where there is actually some response. It's not very much force, depending on the detail, and there can be some damage if you're not careful. We found, or Kerry found, that she has to have enough gap opening within the track so that the partitions don't engage the end of the track, the anchor, to get damaged otherwise. Larry Feinstock has been working on a project that involves research in Japan, in which and a lot of structures have soft stories. This is just showing a 4-story structure, the weak story. So to overcome that, the structure's already been designed is to provide spine, called a spine system. If you put a spine system in a structure, you're going to alleviate the soft story effect, but the higher modes can still contribute, and they're going to generate high acceleration. So to overcome that, force limiting connections are placed between the spine system and, in this case, a structural system, such that you're able to alleviate the high accelerations and also the soft story. The work that's being done at Lehigh is to develop these connection details in order to promote the resiliency, develop a design procedure, perform hybrid simulations. In this case, it doesn't have to be in real time, to assess the performance and design procedure, as well as the performance of the connection shown here. There's a DIC system measuring some deformations, conducting numerical studies as well. And then that will follow up in December, full-scale shake table testing eDefense. And you may have received an announcement from eDefense about a blind prediction contest. That's associated with this project. Here is a split screen video showing the structure. The spine is not exactly shown, but it's along the cursor here. This is the force deformation response of the connector down here. This is not moving because it's a still picture. We didn't take a video at that time. And this is the displacement through the 4 stories. Essentially, the system had very small amount of residual drift, which otherwise you'll see in a minute. This is a system with the spine. This is from the numerical simulations. This numerical simulations without the spine, with the spine, the hybrid simulation. Without the spine, we get the soft story here. With the spine, that's alleviated. Plotting the story drift time mysteries of all 4 stories. You see the MRF shown here. You're getting residual drift. This is detrimental. The building's going to be basically demolished, even though it didn't collapse. This particular level of earthquake loading was actually the max considered earthquake, so it may be more demanding, but it shows the spine system works well. And here's that response. The accelerations, accelegram from the earthquake shown here. You can see the reduction when you compare the numbers in the last column here. The MRF alone has smaller accelerations, but it has a soft story, which is bad. Adding a spine, you're able to reduce the drift and also not increase accelerations too much. And then lastly, this is one of the latest testing that's been ongoing in the laboratory, is the seismic resiliency of equipment, basically multifunctional floor isolation systems using hybrid simulation or cyber physicals, led by Scott Harvey at OU. We're up and running, fully operational, so he was able to come and do these tests almost 3 weeks ago. He was here for about a month doing testing, so his testing actually finished 2 weeks ago. He came here at the beginning of August. He's looking at multi-directional nonlinear dynamics of these systems, FISs, to promote, again, resiliency, develop a rigorous design methodology in order to incorporate these devices into buildings and their interaction that may occur. Shown is conceptually the system on the left and the isolation system on the right. We're performing characterization tests for Scott that he can validate his physics-based models, but also hybrid simulations as shown conceptually here on the right side. These are, during this test, both Scott and the student were here. And this is our control room. At the time we elaborate on, but we had to be very careful about following CDC protocols. We have social distancing, but otherwise we're able to operate. These were the bearing and characterization and the hybrid simulations. These are some results here. Okay, well, thank you very much.
Okay, we will break for a Q&A session right now. So if anyone has any questions, you can unmute yourself or raise your hand in the participants panel or type your question. We'll take a minute break for questions. I do want to note there was a comment in the group chat sent to me privately. Will the recordings or the PDFs be made available? Yes, after the presentation today at some point, probably by Monday, we will have on our Lehigh Design Safe website, there's a workshop section, and we will be providing links to all these presentations. And later on, we have a recording of this if you want to go back and view that as well.
All right, looks like we don't have any questions, or I think maybe.
Yeah, I was just.
Hello.
Yes, hello.
Sorry, I have a question. For the slides that you showed, the concept of the hybrid simulation with in the wind hazard test. Okay, so for the experimental one, we have the damper in the lab. Okay, you will get from the damper the force and displacement, right? At the same time, you will update the numerical analysis, right?
I'm not sure I follow your question, but if you're using model updating, it's in real time online model
Yes.
updating. And Liang Cao will actually explain that a little bit later.
Okay, so I will watch it later. Yeah.
Yeah, so I don't mean to be too terse there, but basically it's real-time model updating in which the parameters are, there's 3 of the parameters, and those parameters is a basic assumption or hypothesis that the model is as such, but those parameters are updated based on the measured response of the specimen that is in the laboratory.
Okay, thank you.
Yeah, thank you.
If there are no other questions, I do not see any in the chat, we can continue. So Liang, you can proceed to share your screen and unmute yourself and proceed.
Let me see if I can. Share my screen.
You see, okay, on the bottom, you see your green share screen button.
Yeah.
Okay, great.
Let me check. Okay. Can you see my screen?
Yes, we can. Thank you.
Okay. Thanks. Good morning, everyone. My name is Liang Cao. I'm the NHERI Lehigh research scientist. Today, I'm going to explain you the concept of the hybrid simulations, including its framework and hardware and software capabilities. So Dr. Rickos already explained a little bit on the overall concept of the real-time type simulations. Basically, it consists of 3 components. One is the analytical substructures, where you model something the structures you modeled in the computers, and the experimental substructures, any experimental specimens, for example, as dampers, you modeled in the lab. And the simulation coordinators is just used to integrate the equation of motions by assumed excitations and calculated real-time structure response. Why we are doing a real-time type of simulation? First, it is the cost-effective methods comparing with full-scale dynamic test, like a shaking table test, because you only physically model the partial of the structures. It can significantly reduce your cost for dynamic testings. Another good benefit on it is you can do various analytical substructures on one single given experimental substructures. For example, if you only have one physical dampers, you can assume these dampers are installed in different type of structures, low-rise building, high-rise building, and then you can conduct 1,000 type of simulations. Last, for the hybrid simulations, it meets the need of the natural hazard engineering communities by providing experimental validations on the concept for natural hazard mitigations. And the great advantage on the real-time hybrid simulations is it can account for rate-dependent physical specimens. For example, some rate-dependent structures such as friction damper, viscous damper, base isolators can be investigated with real-time hybrid simulations. They are not possible with the conventional slow hybrid simulation because their dynamics is related with the rate, and the dynamic could change if you have a really slow velocity. So for the overall concept of real-time type simulation is pretty easy and straightforward. However, if you want to do the implementations, you gotta face some issues and challenges. The first one is in the simulation coordinators, especially on the numerical integration algorithms. We want the numerical integration algorithm be accurate because every dynamic test or analysis are approximate analysis. We want to have minimize the errors, give you the realistic and more correct answers. And the second is we want to have we prefer to have an explicit numerical integration scheme. So basically, the integration scheme can characterize as classifies as implicit and explicit. The explicit scheme means the for the structural response in the next step is only depending on the functions of current step and a previous step. The benefit is it can avoid the iterations during each time step. So the iteration, sometimes if it's not converged in each time step, you can't even do a hybrid simulation. If you use explicit schemes, we want this scheme to be unconditionable stable. Because, like, for example, if you want to do complex analytical substructures with highly nonlinear behavior, some high frequencies could give you could destabilize if your integration scheme is conditional stable. A lot of explicit schemes are actually unconditional stable. And then for the last challenge, we want the integration scheme to have the energy dissipation function, which means the numerical energy dissipation, because we could always get errors during the hybrid simulation. Those errors can come from the noise from the load cells, and also can come in from the state determination procedures for giving a large time step. And the second challenge is we want the simulation coordinators can have a faster communications, which is it depends on the test equipments we gotta explain later. And the challenges in the analytical substructures is we want the analytical substructures are able to providing a fast and accurate state determination procedures, which means every time when we are calculating restoring force, we want it become fast and accurate. If we can do that, then we can model more complex and nonlinear structures. As long as if we can have these abilities, the results is more realistic since we are including nonlinear behaviors. The challenges in the experimental substructures, first is the scale. So the scale matters. Every time we prefer to do a large scale or full scale. So if you want to do a full scale hybrid simulations, then we need to have the large capacity of hydraulic system and dynamic actuators. Dr. Rickles already explained in the equipments in Lehigh lab. So we can using our large dynamic actuators to overcome these issues. The second one is we need actuator kinematic compensations. This is, for example, for large-scale experimental substructures, sometimes your controlled node or your imposed displacement is not exactly the same locations on the actuator connections. And it will require some kinematic compensations. I gotta explain this later. And the third challenge is we need a robust control for the dynamic actuators. This is basically coming from the, we need to compensate the delay in the hydraulic and also the amplitude, displacement amplitude errors. So here is our Lehigh, we come up with the real-time hypersimulation implementation solutions. The first one is for the integration scheme. In Lehigh, we developed and proposed several unconditionally stable explicit integration algorithms. You can find those algorithms in these publications. We have a basic 3 publications listed. For the most recent one we used, we call it NHERI method. So it is one parameters integration scheme. So if you look at the equation here, is the first 2 is velocity and displacement update. It's pure explicit, which means for your next step response is only depending on the current step. And then we adding these weighted equations of motion to introduce numerical dampings. So, and you see there are some integration parameters alpha 1, 2, 3. They are model-based integration parameters, and they are fully defined by using one single parameters we call row infinity value. So how does the row infinity value represent? So the row infinity value represents the numerical dampings. If you look at the graph on the right, this is controlled numerical damping. So the x-axis is the big omega is the natural frequencies times the delta t. So this is single degree freedom examples. And the y-axis is the equivalent damping system. So if you have a rho infinity equal to 1, so you will always have a 0 numerical damping added. And rho infinity equal to 0 under low modes of response, you have a pretty much like close to 0 numerical dampings. If you have a higher frequency response, then the numerical dampings increase and it can almost close to 100%. So you can adjust these rho infinities to damp out any undesired high frequency response. So basically this rho infinities is the only one parameters you need to define before the simulations. All these alpha 1, 2, 3 are pretty defined based on the rho infinities. Well, and the rho infinity value is from 0 to 1. Second one is for the finite element modelings of analytical substructures. We developed a new explicit force-based nonlinear fiber element. So typically we used a fiber element for the finite element modeling on the any numerical structures. And it can categorize by displacement-based fiber element or the force-based fiber elements. So the benefit on displacement-based fiber element is the state determinations is straightforward. However, because the displacement-based fiber elements, they relate on the shape functions, the curvature varies linearly. So that which means if you want to model the nonlinear behaviors, it requires numerous elements per single structure members. And it can significantly increase the number of degree of freedoms. If you want to model a high-rise building or more complex structures, then you gotta give a really large burdens on the computers. Sometimes you can't even achieve the hybrid simulation or real-time simulations. So that's why we prefer to use force-based fiber elements. The benefit for force-based fiber element is the equivalence is strictly enforced. That means the material nonlinearities can be modeled using a single element per structure members, and it can significantly reduce number of degree of freedoms. So it's suitable for the real-time hybrid simulations. However, it has its own drawback. So typically, most of force-based fiber element requires iterations at the element level. So it will jeopardize the explicit integrations. That's why we propose a new type of fiber element we call explicit force-based nonlinear fiber element. First, you can find these elements on these publications in Journal of Structural Engineering. So the first benefit is this one is explicit elements. So can be used with explicit integration scheme. And also it's forced fiber element. So it can significantly reduce the degree of freedoms on the system modeling. And the one significant achievement we have is in these elements, we fix the number of iterations during the state determinations procedures. And we carry over the correction of unbalanced section forced into the next time step. So here is the examples we are using the explicit force-based nonlinear fiber elements to do the real-time time simulations. We are doing a real-time time simulations in a 2-story reinforced concrete buildings subject to MCE level earthquake. And for the experimental substructure, we're using the nonlinear viscous dampers. We assume the nonlinear viscous damper is installed in the 2nd story in the middle bay. And this 2 graph is the moment curvatures on the left corner column on the 1st stories. And the top right graph is the damping force displacement loop, which represents its energy dissipations. So basically, this tool graph on the left bottom is the roof displacements on it's bidirectional roof displacements. But most interesting we're looking at is the moment curvatures on the first story columns. You can see the columns develops a highly nonlinear behaviors with cycling strengths and stiffness deteriorations. So, and a lot of pinches happens in the force deformation response. It demonstrates the importance why we have to model the structures as a nonlinear elements. The third a great achievement is we developed methodologies to do a real-time nonlinear model updatings for the real-time hybrid simulations or even hybrid simulations. What that means is, for example, on the last testings, we're doing a two-story buildings with one physical dampers installed. So if we want to do a like complex or high-rise structure, then we may need like more than one dampers or physical elements. We could be using a dozen elements. However, due to your lab space, sometimes you can't fabricate all this all the physical elements in your lab. So what we can do, so we can actually numerically model partial of the physical elements in the analytical substructures, and we are doing a real-time model updatings based on the existing experimental elements. So the basically means the dynamic behavior is keep updating in real time using the experimental restoring force feedback. I'm going to explain this through an example later. The fourth great achievement Lehigh developed is we developed 3D kinematic compensations actuator control algorithms. So what that means is sometimes if you have a really large scale experimental substructures, for example, for this CLT project, we have 4 actuators to controlling the CLT panel. However, your control node is actually on the panel, but not on the actuator connections, which means you wanna, whatever the command displacement you give it to the experimental substructures is actually for the panel. The control is on the control node, but not the actuators itself. Then, due to some like deformation or nonlinear behaviors, and we need to come up with some compensations to minimize these errors between the actuators displacement and the control node displacement. And also, these compensators also achieve ability to have to. If you look at it, these formulas, this is purely based on exact solutions. So there's no iterations involved. So it won't jeopardize the real-time simulations procedures. It won't slow down any integration procedures too. And you can find these kinematic compensations on these 2 publications. The 5th one is we develop a real-time adaptive servo hydraulic control. This is used for the actuators delay compensations. So basically, what that means is sometimes you always have a amplitude error and the delays. This is coming from maybe the nonlinear servo hydraulic dynamic, maybe coming from the actual fluid dynamic. Sometimes the test specimen material and the geometry nonlinearities can give you amplitude error, and the hydraulic can give you the delay. So what we gotta do? So we try to, on this delay and the amplitude error can create like instabilities for your real-time hybrid simulations. So that's why we develop our own real-time adaptive actuator control. So this formulas is basically explain the controller. So the X, so this X is what we call a compensate input displacement. Oh no, the U is a compensate input displacement to the actuators, and the X is the targeted displacement. Basically, it's follow the Taylor series, and we have 3 parameters: A1, A0 to A2, and this parameter is adaptive parameters. So that means there's no user defined. So these parameters can be automatically adapted based on the minimum delay errors using the least square functions. And there's some physical meanings between each parameters. So if you look at the first parameters, it actually represents the amplitude error. And the first and the second one, the ratio between the first and second one, it represents the time delay. Here is the summaries of our advanced achievements in Lehigh. So in Lehigh, we are able to do a 3D large-scale multi-directional real-time hybrid simulations. To do that, we develop our own unconditional stable explicit integration scheme. And we developed the explicit full-space nonlinear fiber element for the analytical substructure modeling. And we developed a tool for real-time nonlinear model updatings. And we also developed a 3D kinematic compensations and the real-time adaptive servo hydraulic control for the hydraulic actuators. Here, I gotta introduce examples to explain how we're using the message to do the real-time hybrid simulations. So this example is a multi-hazard real-time hybrid simulations on tall buildings. Basically, it's 40-story BRB frame buildings. We assume it is located in the Los Angeles. It is designed by the peer report. And basically, it has a BRB frame on the north-south direction and east-west directions. On north-south direction, the BRB frame are installed in the middle bay. And the east-west direction, there's 3 BRB frames installed in the BRB frame installed in 3 bays. So basically, north-south direction is weak directions. And also, the building itself have 2 outrigger columns connected with BRB frame. And those are only connected on 20, 30, and 40 story. So the objective for this study is we try to replace the outrigger columns by a nonlinear viscous damper to improve its multi-hazard mitigation performance. So to do this real-time hybrid simulations, we're using the MKR alpha integration schemes and the ATS actuator model controls. And also we're also using the online model updating for the nonlinear viscous dampers. I'm going to explain how we do that on the next slides. Oh. For the multi-hazard excitations, we consider earthquake and the wind. For the earthquake, bidirectional earthquake is used. It's a MC level 1989 Loma Prieta earthquake. And for the wind load, we're using bidirectional wind loads we observed from the wind tunnel test. The design wind speed is 110 miles per hour. So the wind load is actually from the aerodynamic wind testings at the NHERI FIU facilities. In their lab, we built our 40-story building as a rigid model, and we are measuring the wind pressures in each wall size and calculate wind force, time history wind force. And know that the rigid model in their facilities actually 1/150th is a small scale model. Then when we are calculating wind force to achieve full scale, we have to scale back the time history's wind load. So right now we are doing, for our hybrid simulation, we are doing a full scale hybrid simulations. Here are some parameter value we used in the real-time hybrid simulations. We're using the explicit MKR integration logarithm. For both wind and earthquake, the time step we're using is 6/1024. This is able to achieve the real-time hybrid simulations. And the only difference is the rho infinity numbers, because for our integration scheme, we only need to change these numbers. Because under wind load, the structures most behave, we predict it will have a linear behaviors. So then we have less numerical dampings than the earthquake, because the earthquake the structure go for nonlinear, that may have some high frequency components come up. Then we need a higher numerical damping. For the ATS actuator control, since the under wind load structure behaviors is pretty first mode dominant, so we fix the A0 and A2 volume. So this A0 is represent the amplitude errors, which is you can easily estimate from the actuator itself based on the measurements. So then we fixed these values. But for the earthquake, because you don't know your actually your structure may have some nonlinear high frequency behavior. So we leave all these parameters adapted. Here are some key features on the analytical substructures. To model these 40-story buildings, we create 1,317 nodes, and also including 2,974 elements, including 2,411 nonlinear explicit force-based fiber elements, which is used to model the beam and the columns, and 11 nonlinear explicit Maxwell elements to model the dampers, and 552 nonlinear truss elements to model the BRB frame. So why we have 11 damper elements? Because we have 12 outrigger columns we want to replace by the nonlinear viscous dampers, which is on 20, 30, 40 stories. So each story have 4 dampers installed in the east side and both east sides and west side. We only using one nonlinear viscous damper in our lab as the experimental substructures, which we assume is located on the east-south corners. And all other 11 dampers, we are numerically models using the nonlinear explicit Maxwell element we developed. And those dampers will be so those parameters in these dampers will be we do the real-time model updating through the hybrid simulations. So there's the procedures. We only using one physical dampers in the 40-story southeast corners, and we're remaining all other 11 dampers as a numerical dampers. When we do real-time model updating, we're using the Anson comma filters tool to update the model parameters. To model these dampers, we're using the explicit non-iterate nonlinear maximum well damper model, because everything has to be explicit. And of course, the Anson comma filters, we have some methodologies to tune the comma filter parameters. So you can, here's some difference on the overall concept. So typically the real-time type of simulations, you just feedback the experimental substructures restoring force to the simulation coordinators, and also the restoring force from the analytical substructures to calculate the real-time structural response. However, because you have 11 numerical dampers, and those numerical dampers need to be more on time, real time, need to be updated. So what we gotta do, we use the command displacement from the experimental substructures, and also we using the measuring the restoring force as an input to the Anson comma filters, and then we update the model parameters in the nonlinear damper models, and we use the analytical command displacement for the numerical damper positions to calculate the restoring force. And this restoring force is analytical restoring force. And we feed this restoring force back to the simulation coordinators and then calculate the equations of motion. Here is the videos on the 3D real-time type of simulations and the earthquake load. So the top graph is actually the top view of the roof displacements. The x-axis is the north-south directions, which is the weak directions, and the y-axis is the east-west directions. It's the strong directions. The second and third graph is the first story north-south direction BRB frame hysteresis response, and east-west direction BRB frame hysteresis response. And the fourth one is actually the physical damper energy dissipations. Is the y-axis is the damper force, the x-axis is the damper deformations. And these two time history graph, the first two time history graph is the floor displacement. here we're using roof 30, 20, and 10 floors. And the last two graph is the actually the bidirectional earthquake accelerations. Okay, so you can see the BRB frame have a highly nonlinear behaviors. That's highlight the importance why we have to do a model it as a nonlinear structures, especially under the MCE earthquake level. And there's the damper itself have a really high energy dissipations here, which is this damper is a full scale dampers. The second video I'm going to show you is the wind simulations. So we assume the wind is blowing from the east and west directions, which is in the y-axis. However, because this is the bidirectional wind load we observe from the FIU facilities, we also have some vortex shadings on the crosswind side. Because this wind load is about like around 6 minutes wind load, so we speed up these videos, and we don't want us watching the 6 minutes videos under wind loads. So there's no sound in these videos. So you can see under the wind simulations, these structures, the BRB frame behave purely linear, have a linear behaviors. That's what we expect. The other thing we find is interesting is even the wind is blowing in east-west directions, which is y-axis. Actually, the roof displacement is coming from north-south directions. This is partially because, okay, the north-south direction is weak directions, and also the vortex shadings affect a lot. So that's highlighting important why we have to do a 3D hybrid simulations. If we only do 2D, we model the east-west directions. Under this case, we are not even able to capture the large roof displacement because they are actually coming in the north-south directions. Here's some key findings. So under the earthquake load, we're interested to look at the BRB maximum ductilities. So this is what we found. After we install the 12 nonlinear viscous dampers, we can have a maximum 30% reductions in the north-south directions, BRB frame, because the damper is only installed in north-south directions. So we don't have that much reduction in the east-west directions. But it's a pretty good achievement because we're only using a 12 nonlinear viscous damper in the 40-story buildings. And for the wind load, we are more focused on the roof accelerations because it affects the comfortables of the people who live in these buildings. So we find out after we install the nonlinear viscous damper, we are able to reduce a 35% peak accelerations in north-south directions, and even have a 10% reductions on the east-west directions accelerations. And for the RMS accelerations, we have even close to 50% reduction in north-south directions. Thank you very much.
Thanks, Liang. So Again, I will open up the forum to questions. You can type in your question in the chat, or you can unmute yourself. I see there was a question early on during your presentation regarding compensation. The question is, do you need to calibrate alpha parameters from pilot experiments, or are they obtained only from numerical structural information? Question.
So I think the alpha parameters, you are talking about the integration scheme, right? So if you are talking about the integration, the alpha 1, 2, 3 is actually predefined by the low infinity numbers. You don't have to do anything calculations on the alpha parameters.
Okay. If there are any other questions, take a moment to unmute yourself or write in the chat. We'll give a moment for that. Okay, if there are no other questions, it seems thank you, Lang, for that. We are going to proceed next with the IT operations and cyber infrastructure portion of the facility. And I'm going to bring this up again. Okay, thank you. Again, I'll reintroduce myself. I am Thomas Marullo. I am the NHERI IT Systems Administrator and Software Developer at the NHERI Lehigh EF. I've been at Lehigh since 2004, since basically the inception of the NEAS phase, and developed the architecture and infrastructure that helped create a successful NEAS Lehigh facility. And then we brought many of those aspects to the NHERI phase and further developed them into a more successful applications for projects that we're doing now. So I'm going to review the IT operations and cyber infrastructure of the facility. Let me start my slideshow. The overview that we're going to go through today about IT and cyber infrastructure, not just computers, but how we use those systems for all the aspects of a researcher coming on campus in our facility to be trained on how to use our system, what each of the components are, and how they are useful for when you're conducting your experiment and even just planning stages, and how you're going to use the equipment. We're going to go into a little more detail on a technical point of view of how hybrid simulation works and why it's important to have a robust and high-speed IT infrastructure set up. And then we'll talk about, importantly, data management. When you are conducting an experiment at the Lehigh Experimental Facility, what are we doing with your data? How do we ensure that your data is obtained correctly, is organized correctly, and then managed with us and at the Design Safe facility, where ultimately it goes into their data depot for you to publish and curate and publish for your DOIs. So let's begin with the researcher training and experimental support that we provide at the Lehigh Experimental Facility. First, when you have your project and when it's proposed and you're able to conduct research at the facility, us and yourself, the NHERI team, will work together on these aspects of training, development of the experimental protocols, which may take a long time, instrumentation that you're going to either bring to our facility or that we have available. So Dr. Ricks has provided a long list of sensors that we have available at our facility for capturing data for your experiment. And then we'll discuss control and safety plans and how do you feel the experiment that you're bringing, whether it's newly constructed or payload, how it's going to be controlled in our laboratory. What equipment do you need? You see that we have a variety of actuation systems, larger, smaller, high speed. And then what happens in cases of failures? How do we prevent people from getting hurt? How do we prevent your specimen from being destroyed prematurely? So we look into that, and we spend a lot of time discussing that. And now we do that over Zoom and eventually in person when, with COVID safety protocols that we did recently with Dr. Harvey on campus. So once we have our team and our collaboration set up, we use the Design Safe tools to create a project workspace, and that allows us to collaborate. So it's basically a cloud storage area that is going to eventually be used for your curation and publication on Design Safe through their data depot. Design Safe provides documentation, and they recently did a webinar on how to use the data depot, what tools are available, the publication capabilities that they have. So we work closely with them on developing and integrating our site with theirs and the data modeling. Just yesterday, we had a very long data model discussion about how we can improve hybrid simulation data modeling. So we're always working with them. We're going to work with you on curating your project to make it a success so that later on when you publish it, you have a great detailed DOI that you can present to the community. When you're on site, we do a laboratory walkthrough, and we identify all of the IT systems that and servers, hardware, equipment that we're going to be using, and we provide demonstrations. Recently, we've had Dr. Harvey come in, and this is a COVID world right now where he had been quarantined for 14 days, comes in, and we follow strict protocols of social distancing and cleanliness. And we walked through and did demonstrations on how the instrumentation worked, how the data acquisition control and simulation systems along with the telepresence work, for example. If we can't do on-site walkthroughs, we have provided a virtual tour of our facility that is available at the Lehigh Design Safe homepage. It's about a 13-minute video that you can go through all of our facility and see the laboratory virtually walking through it. So I recommend, if you want to see more video of our facility, please visit the Lehigh Design Safe webpage, and then you'll see that video there. It's worth your time. And so as we develop that project, we go and we validate the control configurations through numerical and hydraulics off simulation. What that means is we physically develop the system in our control architecture, but we don't turn on the power to the actuator. We can simulate that through numerical processes. And we do that to make sure that the control makes sense and that your simulation will work in a simulated world. And then once we're ready to move forward, we configure our data acquisition system for sensors. If you have, for instance, position sensors, we will go and physically move all those position sensors to make sure that they're giving you the proper results and the proper polarity. Direction is very important, especially in a hybrid sense when you're looking at a global model and then you're converting them to the local coordinate spaces. We need to make sure that your data acquisition is providing the correct results and polarities. And then video acquisition, whether you're on campus or off campus, having video of your experiment in multiple angles is very important for understanding what's going on in your in real time or later on by post-processing that data. And if you're off campus, if we have to perform a test for you off campus, we have video that we can you can HD streaming video to your site that you can watch along and perform your experiment virtually. Again, data streaming, we have the ability to stream that data and form plots on your screen as well. So a lot of good telepresence capabilities and safety protocols and for the equipment. And see, we spend a lot of time even just discussing this slide, but eventually you get to conduct your experiment, and when everything is configured safely and properly, we can be successful in conducting those experiments and then eventually take that data that we've acquired and archive that on the Design Safe project space that we have. It's actually called Data Depot, not Project Warehouse, but regardless, semantics. And then finally, the research team processes that data with the tools that Design Safe does provide. I mean, they did a webinar last week about how they use their Data Depot and the tools that they have available. So let's go and take a deeper dive into the IT infrastructure. This is a video of this is a picture of our control room, and I'm going to detail what you see over here. So my mouse is there's the pointer and the pen here. I think it's a little bit better to see the pointer, excuse me. Here's the pen. Right, so data acquisition on our left. We have our simulation space over here with our overhead video screens that we could take multiple videos up. On the right side, we have, you see my pointer, we have our telepresence, our 2 camera servers, and on the right, you could see our control station with the hardware that we use for controller and simulation. So as we move forward, we dissolve that into a IT infrastructure that we've developed here that's based on a protocol called SCRAMNet. SCRAMNet GT is a synchronous common random access memory network. So a high-speed fiber optic based network for transmitting low-level data in an address space. So if you think of Ethernet, you think of like your local area network. This goes even deeper down the lower protocols where it's high-speed fiber optic, instantaneous synchronization of data on a network through nodes. So data acquisition, control, simulation, they'll all see the same data at the exact same time within hundreds of nanoseconds. So this is very important for being able to have that real-time control and being able to synchronize to the millisecond of data coming from your data acquisition to your controller. So again, we will zoom into what our data acquisition is. We briefly went through this. We use a Pacific Instruments 6000 USB-based data acquisition system. It has 3 chassis. Each one of those has up to 16 modules that can have approximately 8 different channels of data, and those channels range from voltage acquisition with excitation to strain of quarter bridge to full bridge circuits with thermocouples. So we can vary the amount of data acquisition that you need for your experiment, and we can have a wide array of different sensors and equipment, all scanning at the proper rate of 4 kilohertz for real-time testing. We scan at 4 times the control rate to prevent aliasing of those signals. Control system that we do have multiple control systems. So RTMD, CTRL, and I'll take a step back. A lot of our things are prefaced with the RTMD preface with what they're defined. So CTL1, CTL2, or CTRL is just noting the types of controllers that we have. So primarily we use the Servo Test Systems Pulsar Hub control system. It's a servo control system for hydraulics. Mainly it provides you your PID control loops. And we run that at 2 kilohertz for a more fidelity on our control rate. We have recently implemented the Cyber Physical Small Structural Laboratory through another Pulsar hub system, and that gives us wider vendor support. So instead of using the traditional 5 NHERI actuators that we have that were provided from Servotest, we can now interface with the MTS actuator systems, MTS load cells, and other actuators as well if we need to. So this system is very useful for us. And if you come in and you want to do something more advanced, for instance, with National Instruments sensors, you might have your own data acquisition system in a National Instruments system or Veristan. We have a Wyman inertia control system that is they're in a LabVIEW solutions provider, and they have their own controller, a PID controller that interfaces with National Instruments modules. So we can access both worlds of hardware and give you a lot of capabilities for control. Let's talk about simulation and what's important here for actually operating real-time hybrid simulation, or just an experiment in general, like our CLT panel, which isn't a real-time experiment, but we use this architecture for that. So we have a host target configuration, which means that you have a computer that's your workstation and a target that's going to operate your software. We have a Dell Precision workstation, so that the control system and the UI is going to be fast and responsive. And then we procure SpeedGo performance real-time targets. We currently have 4 of them in our laboratory that we've obtained over the last 10 years. And these are high-speed Intel-based processors that are going to perform. They have multi-cores on them, so we could do parallel processing. But they're high-speed systems dedicated to just executing your code in real time and ensuring that the deterministic capabilities of simulation. So let's look at the simulation coordinator, which is the name that we tend to use in our data models. What is operating your experiment? There's a MATLAB Simulink interface that we primarily use that will control the rate of your experiment or control how we impose commands to targets or actuators. And we're able to use that and remotely log into that for hydraulics on, hydraulics off testing, numerical simulation, and post-processing data that we can look at quickly after an experiment's done. We could dump data from our target systems and view it in a Simulink world or in another program that allows us to view plots that you're seeing on the screen very quickly and analyze that. And what we call RTMD XPC. So XPC is the legacy name of a real-time workshop for MathWorks software. So we still use the name XPC for our targets. They are SpeedGo systems, and they provide parallel processing and fiber optic communication and other types of industry protocols. So if you come in and you need to use a different type of IP industrial protocol, we have capabilities of interfacing with them as well. And those we have, SpeedGo provides modules for interfacing to different hardware, whether it's National Instruments hardware or their own types of analog to digital components. And it's a bring your own model type of infrastructure. So for instance, I'm referencing them again because the most recent OU, Scott Harvey, he brought in his own model and he just dumped it into our system as a validated block that we executed. And I'll explain how we do that in a moment. But first, let's discuss in the technical point of view how model flow through real-time hybrid simulation works in our Simulink simulation. So we discussed, Dr. Cow and Dr. Rickles have discussed what the integration method is, the MKR integration method. And at a technical level, what are we doing? So at the time zero, right when we start the experiment, there are calculations done for x dot, which are your commands, and displacement and velocity commands. At the beginning of that integration step, we need to look at the hybrid simulation. In our case, we might be running a viscous stamper on the lab floor in a tall 40-story building. So what do we have to do? So we need to separate the command coming out to that experimental component and its local coordinate system. But at the same time, we need to calculate that state of that 1600 degree of freedom model on our real-time systems. So the problem is, though, it's going to take a long time, and a long time meaning 6 milliseconds, to calculate that computational model. Our actuators don't want to have a start-stop where they stop, and then where you impose a step command and then you wait for the next 5 milliseconds, because our systems are rate dependent. So what do? Well, we separate the command from the computational model, and we let our actuator just have its own inertia. We maintain that linear ramping through the actuator control, and then at the same time, we're computing that. So we're doing a parallel process during the integration state, and then at the end of that 6 milliseconds, both systems, both the experimental component will receive its data back from the data acquisition, i.e. it's returning back its force of the load cell, converting it back to a global system, along with getting the full response of the 1600 degree of freedom model. And then we form that back into a total restoring force vector that gets fed back into the integration algorithm and forms an acceleration for the next step. So now your model knows what is going to be the next state of the system. And then we close the loop on that and repeat that whole process again. So that's the flow of how integration substepping works in the real-time hybrid simulation. And we've implemented that in Simulink. So this is a representation of what our Simulink models do for our hybrid FEM software that was briefly discussed, is where in the initial time synchronization, we calculate some target displacements and velocities. And then those get sent to both the numerical element calculation that's being done here, along with your experimental substructure. And like I mentioned before, bring your own code. This gray block can be replaced by your own validated block, which just accepts displacements and spits out restoring forces, whether it's numerical or experimental. Now remember, real-time hybrid simulation can have a number of numerical elements and a number of experimental, not just one. So we can do that and then drop in whatever you need in here, and then all of that gets returned back while recording displacements, velocities, and accelerations and responses of the system for all the degrees of freedom. So this is all implemented in our simulation. And what was Dr. Rickles or Dr. Cal even mentioned, if you have larger models that all don't, technically when we use the word fit into the memory core of a real-time system, that's why we have multiple XPC systems. In our case, we could use ScramNet to synchronize those systems and provide a ground motion that is going to send commands across 2 or more XPCs where you are splitting your analytical substructure. So for instance, say we need to do an 80-story building. Well, the first 40 stories fit inside one, the second 40 stories fit inside the other, and allows us to do that computation over time. So we can expand our capabilities and have larger scalability in our experiments. Again, I talked about safety limits. Safety is very, very important. And when we had, I wish I had a video because it would be really interesting to see. I don't have that here, but Dr. Harvey, when he was doing his base isolation systems, we built in safety limits that in case we went past a certain displacement limit, the test stopped. And he had complete confidence and success in pushing the limits of his experiment, knowing that if we did hit a limit, our safety features would catch that and provide no problems for the experiment, and then return everything back to its resting position. So we have layers and layers of safety simulation built into whether it's software or physical limits that are on the specimen, like hard stops that you would see in actuators. Let's talk about the telepresence system. We have a number of systems here that allow you to visualize your experiment locally and remotely, whether it's in our facility or through Lehigh, the infrastructure that they provide. Excuse me. Data streaming. We use the open source data turbine ring-based network buffer, RBNB. It's technology that was brought into the NEAS phase that we continue to develop on and use. And what that does is it takes data off of the ScramNet and puts it in a ring buffer so that you can store that data on a network and then view it remotely with a viewer that will be able to move into that data based on a time step. So you could view data using the real-time data viewer, which is a Java application that can be run on any system. And again, this is a legacy software that we've continued to maintain and provide support for at the Lehigh facility. And this will allow you to view data in a real-time sense, or you could go back in minutes before, say, oh, what happened? I want to see what that data is. Well, while you're running an experiment, you can't just say, all right, pause the experiment, let's go look at the data. No, we continue to run our experiment and then backtrack a little bit in the data viewer and see, well, what happened at that point in the experiment. So very good tools that we have that are available remotely, locally and remotely for users. Photo and video capabilities. We've procured 24 high definition 4K right now, these are 8K Amcrest bullet cameras, or PTZ, pan-tilt zoom cameras, that we could put as instrumentation into your setup. So you could put these at different points into your system and be able to record video and visualize your system using our capabilities in our control room. Now, the reason why we have that is because when you come to our facility, you're like, all right, I'm in your control room, I can't see my specimen. Reason why is safety. We need to be in our control room, but then what's the problem? You can't see it. So we have 24 cameras up with these large screens that you could zoom into parts of the experiment that you wouldn't be able to just see with the naked eye while you're out there. So it's very important to have a lot of visual technology in our room. And then we have various other cameras for recording video as well. And Lehigh does provide cameras if we need to rent out. And we're using Blue Iris as our backend for doing camera recording and streaming. It's a robust system for allowing us to record record video and audio, and to store them synchronized into a buffer, and then later on stream them if we need to. People could come onto those web services and be able to see archived experiments as well. Let's talk about data, and then we're gonna start to wrap up this conversation on data management. And we have a Synology-based system that stores all of our data that we collect at Lehigh. Now, this is connected to our local area network. Currently, we have about 50 terabytes of data. Each one of those bays has 8 terabyte hard drives that is set up in dual disk redundancy manner, so that if one or two of those drives fail, that your data is safe, and that we could quickly replace. As I keep on hand another 8 hard drives to mirror those other drives, just in case the data goes down. I go in and quickly replace that. As you can hear, there was an earthquake at my house right now. My 7-year-old in the background dropping a giant easel. So we're going to ignore that. And so this is a network attached storage system that anyone on campus, and it's restricted to on campus for that subnet. So if you're familiar with network design, we're only restricting it to the subnet of people that are on campus, not even the VPN, it's people that are on campus. And I'm going to discuss briefly how this is mirrored to design safe through Globus. So there's going to be a little bit more technical details on how we take your data and put it into the data depot without you having to even do a thing. So data management plan, let's talk about this. And this is going to be the final slide to talk about how we handle your data. Is, again, we talked about, we have that local repository for managing that data, especially for risk mitigation. We don't want to lose it. We also have, through Lehigh, Google Drive and CrashPlan, 2 backup services and cloud-based services that we can use. So this is a chart of how our data is managed. And we're going to look at the simulation and data. And these are the ones that I mentioned in our IT infrastructure. This data, we pick locations on those drives. So for instance, we run a simulation on our system. That folder is automatically going to be synchronized to our Synology system. And it's also synchronized to Google Drive. 2 points of offsite, local backup and offsite backup. Now, if you've heard in data management, there's a 3-2-1 rule of 3 different backups, 2 on-site, 1 offsite, something like that. So we're using that plan to make sure that data is stored. So this data is stored on our Synology system, and we partition our Synology to NHERI projects, archives of our old test data or documentation that and then backups of our system. And then again, like I mentioned, Globus. Globus is a tool that's provided to transfer data from system to system, what we call endpoints. So we set up a Globus job on our system to take your NHERI project data and synchronize it to the data depot automatically. So once your project is created, and again, step 1 or step 2 in our project is to create a design safe data depot project. That data is mapped. So a drive on the Synology is mapped directly to your project so that you don't even have to worry about uploading your data. It's done automatically. So we make sure that we have a good data management plan for saving and archiving your data. So eventually that you don't have to do a thing with it. So we adhere to retention policies that Lehigh provides, and the NSF data management for keeping that data online. Eventually, we want to get rid of it because we're going to not need that data. So after 10 years, we can either give it to you or leave it at DesignSafe, but it won't have to exist on our systems longer than 10 years unless required. And under the NHERI Lehigh data management umbrella, what are we archiving for data? Well, during the experiment, we're going to be archiving that raw or unprocessed data that comes from the XP, the real-time systems or the data acquisition systems. We keep that. Reason why is what happens if you have a calibration factor mistake. We can always go back and recalibrate that. You don't want to just take the processed data and then not have ability to go back. So then we take that along with the converted and derived data sets that you might have gotten from the experiment or post-processing that. Again, there's the largest amount now. I find that the largest volume of data size-wise is going to be your video and experiment. High-definition video takes up a lot of space. So we store that along with computational models, whether they're in ANSYS, OpenSeas, Hybrid FEM, whatnot. You pick that. We're going to archive that and whatever scripts that you have for doing. And then we try to maintain the same folder structure along with appending the test name and date so that it's easy to search for what test you're looking for and what data was performed with the data description. So we're going to try to adhere to what the DesignSafe data depot model is that we've helped implement through the Lehigh data model. And again, I had talked, Globus is used for automatic project data upload. Globus can be, it's free to use, and it's something that we set up and provided details to other sites and to DesignSafe on how to share that information with other sites. How do I use Globus if I want to do it on my own site, or bulk download data from the DesignSafe site? And eventually, the final step, when you're done with us, it's up to you to take DesignSafe, open up their interface, and then curate your model, and then eventually click that publish button. So at the end of using our facility, you have a DOI of the data that we've generated for you at Lehigh and helped you process and curate. So with that, I'm going to open it up to any questions that anyone might have related to the IT infrastructure. I'm going to discard that. So.
I mean, hi, this is Jim. Could I just
please,
make a
go ahead.
comment on that?
Absolutely.
One thing the audience, sorry, Tommy, should be aware of, when you submit an NSF proposal, you're required to have a data management plan. So I think what Tommy was just going over is very important. But at the same time, we recognize it's very difficult to absorb all those details. So what Tommy has done is to go ahead and place a document on our website that has it could serve as a template that you could include with your proposal. So you can download that. And I guess, Chad, referring to, or maybe Tommy, you want to go to the website, you can see where that is. And that will be something that you can use to get started. And then we could help you, if you wish, fill in the blanks in terms of the specific details. But that's actually a requirement by NSF.
Correct, thank you.
Yeah, Tommy, do you want to show where that document is? Leave it up to you.
It's on I could, while we're waiting to see if there's any other questions.
Okay.
It is on the Lehigh DesignSafe site, right? So I could bring that up while we're doing that, but let's see. If there are any, I'm looking at the chat. There doesn't seem to be any other questions on the chat, unless anyone wants to unmute themselves and chime in. I'll show what that looks like right now. On the Lehigh DesignSafe site, we have a resources tab that has documentation along with the data management plan and all the other important documentation that you need to know for writing your proposal or operating with our facility. So,
Tommy, can you just click on that if you don't mind?
Yeah, I will. Sorry. I do want to mention, here is the homepage. Here is the video that I had referenced in the beginning about, I think it's important.
Oh, okay.
So let's go to the data management plan. It'll open up in your browser. It is a PDF. And here we go. Okay, so here's your data management plan.
So you can, I guess the audience could literally just copy and paste, right? They could download that and copy.
Absolutely, it's a free resource. It's a provided resource for someone to know how do I archive the data. And again, I guess I mentioned, we provide that support. So I want to make it simple for someone to come on campus or work with us remotely, that they don't have to worry about how am I going to organize my data. We're going to provide you the structure on how this is going to be organized and make it easy for everybody. And I think, you know, the successes that we've had in the past, it's something that is tried and true process that we're doing.
Yeah, no, I think that's really good what you did there, Tom.
Thank you. Let me put the, I'm going to just bring back the agenda so we could,
Okay.
we're pretty much, we're just about 5 minutes or 7 minutes over where we're at. Actually, no, we're in the QA session right now. So we're on time right now.
I'm wondering if there's any questions from before. I know there was one on the model updating. I didn't mean to be terse there because I thought Leanne would cover it. Again, this is James speaking. I don't know if all the questions were answered or maybe you're still wondering about the question, the answer to your question. Is there anything from before that
from what I'm seeing in the chat, everybody it's been answered. Thank you. Everybody's happy with that. So at this point, I think, Chad, we can move on to you to discuss the site support operations and payload opportunities. So I'm going to hand that over to you.
Okay, let me share the screen for my. Everybody see the share screen? Site support operations.
Yeah.
Does that look okay?
You just have to go in presentation mode.
Yeah, that's I'm getting there.
Okay.
Give me 1 sec.
Good.
Yep.
Is that good now?
Not yet. So Chad, let me just jump in. Are you in presentation mode on your side?
I am, yeah.
Okay, so get out of that.
Okay.
Let's just go under slideshow.
Okay, give me 1 second.
Yeah, see on the top next to animations, go into slideshow. And then just make sure that it presents on your primary screen. So it might be presenting on the second screen.
Correct. All right, let me pull it on the primary screen. I'm working with 3 screens in front of me, so it's probably okay. So this may be better.
You'll just have to share that again.
Let me go to share screen again, and that should be better.
There. Okay, so we still see your PowerPoint. We don't see your presentation mode. I'm gonna try that.
Yep.
There, okay, so
We're good now.
We see you in presentation mode.
Perfect. All right, we're good to go.
I'm okay keeping this. This is okay.
No, Chad, I think you should get, sorry, Tony, go to display settings and flip it.
Okay.
Display settings, the middle top, very, very top, swap.
Is that better?
Okay. Thank you. Thank you, Jim.
Okay, we're good?
Go ahead. You're good.
Okay, great. Apologize for that. Again, this is Chad Kusko. I'm the operations manager for the NHERI Lehigh facility. And I wanted to just give you a quick overview of site support operations available for you as a researcher utilizing NHERI Lehigh facility, and also discuss payload opportunities. One thing to note that's again important is the NHERI Lehigh facility is here and available for your utilization regardless of the funding source for your project. We've had projects between the Nice facility and then the subsequent NHERI facility that have been both privately and publicly funded. The real difference between the two boils down to what funds we're able to utilize from our O&M budget, which is provided by the National Science Foundation, towards your project. In that, an NSF-funded project qualifies for many of the costs to be subsidized through our operations and maintenance budget, whereas a project that's privately funded or publicly funded through a non-NSF agency would be responsible for much more of the costs associated with the project budget. And that's something that we could discuss if you approached us with a potential proposal. We could discuss that in further detail at that time. So we're able to provide support operations throughout the entire duration of a project. We have operational staff, administrative staff, technical staff, etc., funded under operations and maintenance. And depending on the specific phase you're on as part of a project, it would impact, what support or who's supporting you from our facility. The user proposal preparation is something I wanted to discuss first, and because ideally that's our first contact with a interested researcher on one of our projects. And that user proposal preparation stage is really broken down into two steps: the pre-proposal step and the proposal writing step. And we certainly realize there is some overlap between these, and sometimes depending on timing ahead of in advance of when a proposal is due, they may completely overlap. But in an ideal world, you're able to make contact with us early enough in the process that we can help address some things early on and point you in the right direction, and then provide a little bit more specifics as you get closer to finalizing your proposal for submittal. So the pre-proposal stage, we want to emphasize a couple things and some questions to ask yourself. One is just strongly encouraging you to reach out to us. You can use me as the primary point of contact. Most likely what we'll do is turn it over at some point in that process to Liang Cao, who presented earlier as a research scientist, and he would take the lead on working to address, get answers for your questions that you may have, and also work on the budget with input from the various people here at the NHERI Lehigh side. But the thing we want to think about at that stage and for you to consider is, what's your idea, and does it fit within the capabilities of what we have? If it doesn't, perhaps there's another NHERI site that it makes more sense. Or if it does and needs some modifications, it's better for us to understand that early. Do we have the necessary equipment and instrumentation? The portfolio that Jim gave earlier on the hardware side and Tommy on the IT side, gives you a high level understanding of what we have available. And if we have the equipment, we'd like to give a run at being able to support you with that project. Make sure you understand what solicitation you're being presenting for and the deadline. That helps us plan on our end of what information we need to get to you and when, and also impacts the budget discussion that I had earlier. And then what additional information can we provide? Can we provide you either directly or through our website that will help you address your questions? On the website where Tommy just was, there was the kind of the cover interface page, which had 6 or 7 blocks, and including that data management plan, which we clicked on. But 2 of the other blocks are questions for a pre-proposal stage, and also a checklist for proposal preparation. Those were created to help you very early in this process as you're considering NHERI Lehigh. It's just kind of a one-stop point of questions you can ask yourself that we would either ask you, or you want to make sure you're addressing as you're considering whether NHERI Lehigh is the right facility. So I encourage you to look at those in advance if you're thinking about proposing something at NHERI Lehigh, and that may help you formulate some thoughts or generate some additional questions that you want to bring to our attention. So if we conclude with the pre-proposal stage, and then we move on to the proposal writing stage as you move forward. The first thing I always encourage is, especially if it's an NSF proposal, is to review the latest version of the NSF proposal and award policies and procedures guide, and specifically chapter 2, which is proposal preparation instructions. And then I encourage people to review our NHERI Lehigh facility user guide. That's another box that was on that interface slide that Tommy had shown from the website. It contains a plethora of information regarding our site, and is really a one-stop shop to help you get some information as you consider our site. The last thing, again, just to reiterate earlier, is just communicate with us as a facility. Again, you can start with me, and we'll get Liang and Tommy involved as necessary. Derek Fritchman, our lab ops manager. Jim may be engaged at that point, depending on the technical aspects of the project. But again, we just want to set this up for success, give your proposal the best chance for funding, and give our site the best opportunity to prepare for when funding moves forward, that we understand what's coming into the laboratory and can schedule it appropriately and budget it appropriately, and help you execute it appropriately. Other information that's important: research plan, facility, equipment, schedule, budget, data management plan. Those are things, again, even if they're not fully detailed, that we would want to discuss earlier in this process. The research plan, just at that point, a general work of the plan, general plan of the work being envisioned, and the support needed by our facility, and then a description of the methods and procedures. Why that's important is one thing that we do have at NHERI Lehigh is a lot of experience in the different positions. Tommy's been here through the NEAS operation. Jim and Richard Souse have been around. Derek Frischman's been our lab ops manager for many years. So there's a lot of experience in running different projects in our laboratory, and having that experience to just bounce your proposed concept off of that our team may be able to look at and maybe, you know, throw back a constructive feedback or a critique that you could consider to maybe modify the design even at the proposal stage. It you know, could just help things move along easier later in the process, and also give you a better vision as the proposal's moving forward. With respect to facilities and equipment, again, what resources are required of our facility? We have an idea based on a short-term and a long-term calendar of what projects are awarded and funded, and when generally they need to come into the laboratory, and what equipment might be needed, what instrumentation might be needed. And then there's always other ones that have been proposed and we don't know the funding status that we have to also kind of consider also. So just having an idea of what equipment, how many actuators, et cetera, might be needed, which of our labs may this fit into, that just helps us as we look long term, because there are a lot of moving parts and a lot of moving projects when it comes to new ideas and proposals and things that are out there. We want to make sure we have these resources, that our capabilities are established, or perhaps they're going to require a little development and collaboration between our operational staff and yourself as researchers. And then, are there additional Atlas resources? The ability of us to leverage the Atlas Research Center, which is the home of the NHERI Lehigh facility, and all the equipment in that center, which isn't NHERI funded or NHERI supported, but yet very vital for conducted structural testing, gives us you know, additional capabilities beyond what just our NHERI Lehigh facility has. And if we can find a way to put those to use to make your project successful, we're more than happy to do that. So we can gather that information and provide it back to you as presented. Schedule, you know, very early in the process, we just want to get a proposed time frame. How you know, assuming a project starts at X date, how far into the project are you looking to get into our lab? You know, what phase of your overall project? Is it right off the bat? Is it after analysis is done, or simulations are done, or smaller component testing is done, et cetera? And also, ideally, you know, a physical space requirement of how much space would be needed in our laboratory. And that helps us, again, include that in these longer term capacity planning schedules to help set us all up for success. Budgetarily, again, we have O&M budget that can help support certain aspects that qualify. The items of what qualify what qualify as O&M funded versus project funded is also listed on our website. But again, if it's a non-NSF project, we'd still be happy to run it in our laboratory if we could technically do it. But you as the project itself would bear more cost than perhaps something funded by NSF, where our operations and maintenance budget would help alleviate or help subsidize some of those costs. So if you go to our website, there's more information on budgeting, including some files, NHERI Lehigh rate schedules, both for funded and NSF funded projects. So make sure you're clicking on the proper funding source, depending on who you're envisioning your funding provided from. This will give you an idea of use fee rates to use NHERI Lehigh equipment, instrumentation, and other equipment, and also personnel rates to have, you know, staff support these costs that aren't covered by O&M. Also, that responsibility cost, which I referenced a minute or so ago, is available, and that again gives you an idea of what tasks are fundable by O&M versus the project itself. And again, we can always look at what you're doing, kind of lay out just a list of steps and give you that best guidance we can. And then we could develop the budget accordingly for the cost of you to conduct the testing at our site. We'd kind of back out what the O&M portion of that would be and just give you a budget to include with your operations and maintenance budget. One other thing to consider as the budget, researchers that approach us have varying interests on whether or not they want Lehigh or would like Lehigh faculty or expertise on the budget, or as part of the proposal, I should say. And generally, it really doesn't matter to us. It's really up to the researchers. You know, we're encouraged by NSF to have projects from outside researchers that do not have Lehigh faculty on, and we're certainly comfortable with that. You know, especially if we've seen early in the proposal process what the concept is, so we know that it could be done within our facility, and we're there to provide the support. But depending on whether or not Lehigh is a co-PI, could impact and probably would impact the indirect cost that's required as part of the project. If Lehigh faculty are not on, we're kind of considered a service entity where we're just providing a service of operating the testing facility, and that's subject to a lower indirect cost rate than if a faculty member were a co-PI on your award. And then that would be more organized research by true definition and would carry a higher university indirect cost rate. So there are implications for how the budget's structured with respect to the NHERI Lehigh facility and the PI. And I just wanted to make note of that. So that's something else that is discussed and thought about at the proposal stage. And then I'm just going to reiterate the data management plan, which Tommy and Jim had talked about a few minutes ago. That example one's available for your use to address questions. And again, beyond that, Tommy's expertise is here and Jim's experience, et cetera, to address any specific questions or help you make sure it supports your vision for the project. So beyond the proposal stage, we also have then the project execution stage. So once funding comes in, really all these other phases from project planning through phase 6 are all kind of post-funding support steps. And there's a couple things that we want to make sure you're just aware of are going to be required. And these are driven by the NHERI NCO for each equipment site. So regardless of what equipment site, it's generally these forms, this type of information. They could get modified. They're always kind of a work in progress in terms of the names of them or the exact content, but generally they include the same information over a period of the entire operation of our NHERI facilities. So there's a compliance check, which is kind of a high level, very early in the process. Again, experimental feasibility, safety, budget, schedule, data. It's a lot of things. Hopefully we talked about the pre-proposal stage, and then we can just refine them a little bit at this point because they're a little farther down the process, and make sure we're on the same page with respect to that. There's also a site utilization request form, and this is kind of an agreement between the NHERI NCO and the researcher and us as an equipment site, just saying we agree on the key aspects of the project. A lot of those key aspects would be those same ones listed above in a compliance check, but again, in as much detail as possible so that we know what the researcher wants, the researcher knows what we can provide, and then NHERI as the operational oversight on NSF's behalf is in agreement that this program set up for success. So some things on the experimental site utilization form, description of planned experiments, what resources are needed. Scheduling is always important no matter the scope of the project, big or small. We want to make sure we can find a way to fit it into the time frame that's beneficial for both of us. Special experimental site services needed. We like to look at safety is critical. That's been mentioned earlier. So we'll always review, our technical staff will review the setup and what they envision it looking like, and identify potentially additional safety features that can be brought in to mitigate potential safety issues and risks as part of the project. What this role and responsibility is for both the facility and researcher, and then the data sharing and archiving plan. We encourage researcher training. We can do that in various ways. We could do something virtually. We could have the researcher on site in advance of testing and go through a brief training, half a day to a day training on the aspects of the operations in NHERI Lehigh. We've done them after workshops like we're doing now. In the past, we've concluded these workshops with researcher specific training, or if you're a visiting researcher and you're coming for an extended stay, upon your arrival at NHERI Lehigh, we could conduct a researcher training at that point. So it's fresh in your mind and leads right into your regular research. But having you trained is something that's a critical step in this process. And then there's the experimental test plan and the scheduling. And we have multiple people impacted with respect to our operations manager in our laboratory and myself and the NHERI facility scheduling group. So we want to make sure we're all on the same page and can publicize the expected schedule to NSF, and also make sure that your test plan has the details necessary so that people interested in the testing can understand what's going to be included and when it's going to occur, etc. Our staff is here to provide support during the experimental testing and operation of equipment. It's both our technical team and then our operational team is here to support. And then post-test data archiving, Tommy's available to assist. It is the researcher's responsibility to upload the data, their own test data, to the Design Safe archive, but Tommy can certainly provide you the guidance on kind of where everything is and how to do it, and then support as you as a researcher get that data uploaded. So information on the NHERI website. One other thing I want to just discuss beyond that free proposal and then post-award support are payload opportunities. We do have a separate location on the website shown here about how a payload project could be established at the NHERI Lehigh facility. And with that comes just an understanding of what tests are active in the laboratory or coming into the laboratory. So you could look at the scope of those tests to see if you potentially have a payload project that makes sense. And then we have identified a payload protocol also on the website that just walks you through the steps of how to go about potentially identifying the protocol. And a big factor in this process is communication with the PI of that original project or that main project to make sure that the PI is on board with this payload coming in and working and being included as part of that project scope. And then again, we can look at the cost implications and what can be covered by O&M, and then what additional funds might be needed for you as the researcher to identify to cover additional costs. And then we can work into the schedule and work on different agreements that we discussed earlier to really consider it as another separate project in our laboratory. So I encourage you, if you're interested, don't have a full-blown project or proposal, but think you have a good payload protocol and idea and looking to see if it fits on something in our laboratory, I encourage you just to review the website there and then reach out to us and we can help you take a look and figure out if there's a good fit. So that's going to conclude my presentation on site support operations. I will stop sharing at this time and then open it up for any questions you may have on that section.
Chad, sorry, before the questions, this is Jim again. Can you elaborate a little bit on the those rates? And you mentioned Lehigh PI or co-PI participation. We got to be sure it's clear that Lehigh faculty don't need to be part of the research team, right? NSF, in fact, is ask us to make sure that that's clear to the audience. Is there a distinction? Can you clarify the rates?
Sure, absolutely. So if Lehigh sponsored organized research rate, so it's kind of standard indirect cost rate is 61% currently is our indirect cost. So again, that would be applied only to the project portion of the budget that we would develop for you to utilize to do the testing at the NHERI Lehigh site. So if you have a Lehigh faculty member as a co-PI on your project, the indirect cost rate applied would be 61%. As a service center where we do not have a Lehigh faculty member as a PI, and we're really just providing operational support, you're utilizing our site, we don't have any faculty involved in the proposal, but we're helping you conduct the research and utilize facility. It's closer to like 41%. So it's about a 20% differential in the rate. So simply that just gives you more direct cost bang for your buck when you're developing your proposal. Your budget will go further, but again, you do lose the having Lehigh as a co-PI if that was something you were looking for. So it's faculty have gone different ways researchers, I should say, have gone different ways when they've approached us. Some are adamant they want a Lehigh faculty on for a technical component of the project. Some are impartial to it, and others would prefer not to and would prefer to just have a lower indirect cost, and it allows them to get a little bit more direct cost out of the budget or keep their overall budget down, whichever way you look at it.
So Chad, what would be typical costs that a researcher may accrue? There are things that are covered by our operations, right? And things that
Yeah,
aren't.
very high level, right? Very high level. Anything associated with the specimen fabrication, having a specimen delivered to Lehigh and having us unload it and store it and relocate it to a test specimen, that sort of thing would be borne by the project itself. Specimen specimen setup, any specific fixturing that we may not have in our inventory that's specific to your specimen would be borne by the project. If we have a fixture that could be reused from a previous test, we'll just do that and save you that cost, and we'll reuse as much as we can. But if there are modifications that need to be made because you have a specific specimen design and we need to attach it to our equipment, that's a project borne, that's a cost borne by the project. And then a specimen demolition and disposal would be also borne by the project. One other thing currently that we have that projects have to bear just because of our budget availability is the cost of instrumentation, of just applying instrumentation and gauges to a specimen. So that's also a project cost. So anything beyond that, moving all our hydraulics, our actuators, setting up all the hydraulics, making sure the hydraulics work, running all the equipment on the test day, collecting data during the test day, attaching the instrumentation to our data acquisition, all of that is borne by our O&M budget and not a cost to the researcher as part of the proposal.
So just kind of in a summary then, I kind of put it from a different perspective because I didn't want to discourage people, so to speak, is that essentially everything is covered by the operations except in a nutshell, the specimen construction, demolition, and any special fixturing. And you mentioned instrumentation mounting. I think our philosophy was, and researchers that have used our facilities typically have they want their students to put the instruments on anyways, right? So they know where they are and how they're positioned. So that cost is really, if anything, is minimal. It's the major cost, I guess, is really specimen construction, demolition, and any special fixtures, right?
Yeah, and we do have instrumentation managers on staff that can help with a gauge plan. Those type of costs are covered in the planning stage for a project. And again, it's really dependent on available budget and interest in the faculty and the researchers. Some prefer our instrumentation managers to work or assist their students or just handle the instrumentation just based on their experience. And again, that cost they just build into their budget, and others want their students to do, which we're comfortable with as long as, again, they're trained and they understand. We want to make sure it's done safely and the data, we're able to get high quality data when we press the go button for actual testing.
So if a researcher wants to develop a competitive budget, like the NSF, they would consider perhaps having their students really just the mounting, the physical mounting of the instrument, the calibration, connection, wiring, that's all covered, I think, under.
Yeah, calibration is covered. The connection to the data acquisition is covered. So it would be more or less kind of running gauges. And if you're just talking strain gauges, applying the strain gauges, marking the specimen, running the cables to the data acquisition. And then once we're hooking everything up and make sure it's checks out and everything, we would cover that under O&M.
Mm-hmm. And I guess the other matter is, like, as a researcher, then we should probably check with you about during the proposal writing process, just to confirm what's covered and what's not covered. So that they
I encourage it, because we'll have to help you put a budget. We'll have to help the researchers put a budget together for that they need to include in their NSF budget or other sponsor budget that would be covered by the sponsor itself. So we would back out all the O&M covered activities based on what we could, how we could best plan it on the information that's available at that time, and then provide for you that breakdown of the budget for inclusion in your overall budget that you're sending the NSF. So that, and again, that portion of the budget would simply be for you to conduct whatever portion of work at NHERI Lehigh you're looking to do.
Yeah. Okay. Thanks, Chad. I asking you as a sort of, from my sense, a rhetorical question, but I think the audience hopefully got some clarity on that. Thank you.
Yeah, absolutely. And again, there's a lot of information we provided here in 2.5 hours, a lot to kind of get your arms around. So if you're thinking about something or just have questions based on what we said, feel free to reach out to any of us individually or send a general email to me and I can get it off to the right person. My email address again is chk205 at Lehigh, LEHIGH.edu. And we'd be happy, if I don't have the answer, I'll be happy to track down the answer for you. Any other questions operationally about this or anything that was covered today? We have about 6 or 7 minutes left. Be happy to address any additional questions someone may have. This was our first virtual researcher workshop. As Jim noted at the beginning, we've traditionally do these in December timeframe on site at NHERI Lehigh. But because of the COVID, we wanted to offer up the virtual. I will follow up with a brief survey that I'll send to you, if not today, then on Monday, and ask you just to take a minute or two and just, if you would, populate that and with your input and send it back. It'll help us plan future virtual ones. Obviously, it's unpredictable when we'll be able to get a large group of people back in the laboratory. Or back into our facility for something like this, a workshop such as this. So we are considering another researcher workshop later in the year with some similar information and some more details in certain areas. So things that you'd like to see in more detail or think you'd really benefit from, if you could provide us as part of this survey that I send you, that'll help us as we consider and plan what a next virtual workshop would look like.
Chad, maybe I could add a point about those NSF opportunities. The division could be whatever researchers have an interest in. It doesn't have to actually be structures. Anything under the NSF umbrella that they fund, you can literally use our facility. So I, as a researcher, I always look for opportunities myself. And there's other divisions besides the CMI, which is associate more buildings. There's CPS and cyber physical systems. So I would encourage people to think about that. Maybe talk to your colleagues that outside of the mainstream. There's other divisions that you certainly, if awarded, you're welcome to use their facility. If you already have an award and you realize, boy, this would have been nice if I would have used the Lehigh facility, you can still do that. It's never too late. So I just want to encourage you to think a little bit outside the box, and any directorate under the NSF umbrella, you're qualified and allowed to use our facility for the purpose that it's there for.
Jim, I'd say one additional thing also. We, as an operational staff, we did complete 10 years of NHERI or 10 years of NEAS and 5 years of NHERI under similar fashion, where we're working with outside researchers. Confidentiality is important to us with respect to protecting your ideas. So if you do come to us with a proposal, it stays within our research team for the purposes of supporting your specific proposal at that time. It won't be shared with anybody outside of the small network of folks that are kind of reviewing the proposal to see if it fits technically and develop a budget, et cetera. So we hope you don't have concerns about that aspect. We understand, academia is a competitive world, but our job is to get proposals into our facility that we can be successful and help you be successful in generating high quality research that you can share within this NHERI community. And that's the way we'll approach, any inquiry that you have. So please don't worry about those aspects. We will protect the confidentiality of your idea and proposal.
Yeah, thanks, Chad.
Are there any other thoughts or questions anybody has?
There's nothing on the chat, so I'll leave it up to you guys to close out when you want.
Jim, do you want to just wrap it up then?
Yeah, so I wanted to thank everyone for spending the time and the effort. Some of you may be in a completely different time zone, for listening to our site. Your interest in our site is greatly appreciated. As I said, we're always looking forward to increase and enhance our capabilities. That if you have something of interest that perhaps we don't have capabilities or it doesn't appear to be, we're always looking to expand. So, please approach us and we'll be glad to talk to you that we can create the infrastructure you need to do your research. If you don't have an NSF project but still interested in speaking with us, you of course are always welcome to do that. There are non-NSF project fees that could be applied, or just outside of the NSF thing, just from a technical perspective, we could always interact. So feel free to do that. And I guess our next workshop, we at this point thinking it's probably going to be virtual again, as I think in December, Chad. However, for December, I think, Chad, the next workshop, I believe it's virtual.
Yeah, we're thinking virtual probably in the December timeframe as of now.
Yeah, and then we'll have as soon as we're able to have one on site. The restriction is our lab is open, but if you travel, there's sometimes restrictions coming from point A to point B. You have to be, go through quarantine, etc. So that's the restriction we have to respectfully deal with. So we felt it's better just to use a virtual one, but virtual workshop. So with that, I want to again thank everyone, and look for, visit our website often. We try to list also publications, ongoing projects, and if you have any questions, feel free to contact us. We'll definitely respond with any answers we can provide to your questions. And I wanted to thank Chad and Tommy and Leanne for carrying the torch. I had to step out for a few minutes because I had two Zooms that I couldn't participate at the same time, and I just had to say hello and goodbye on the other one. So I may have missed a few minutes there, Chad, but anyways, I wanted to thank all you guys.
You're welcome. All right. Thank you, everybody, for attending. And please look for the survey and provide your feedback so we can improve this as we move forward. Thank you.
Yeah, thank you.